Hello everyone. Today we will start a new point, design procedure of turnbuckle. So turnbuckle is a mechanical device which is used to connect two rods. Okay. See, this is a turnbuckle. This image is an example of small turnbuckle which is used to join two rods which both are in tensile condition. So if one rod is connected to at this point and other rod is connected to this point, and after connection, if this middle part is known as coupler, this middle part is rotated in one direction, suppose it is rotated in clockwise direction, then these two rod will get tightened. And if this middle part coupler is rotated in opposite direction, then this two rod will get loosened. Okay, so this device is used basically to tight the two rod. Okay, so to induce the tightness in two rods and connecting these two rods, this device is used known as turnbuckle. Okay, this is a device used. So now we will see a two-dimensional diagram of a turnbuckle. See, the middle part is known as coupler, and the coupler, the point at which the coupler attached to this threaded rod, at which the coupler attached with this threaded part is known as coupler nut. Okay, so coupler nut will be this part and this part. Okay, and middle part at which we have to induce moment to produce clockwise or anti-clockwise rotation for tightness and looseness of these two rods. This middle part is known as coupler. This middle part is generally in hexagonal shape. Okay, to induce a moment. And the coupler nut has a inner surface is threaded surface. Okay, and in this inner surface the rod is inserted, which is also threaded rod. Okay, so this rod is left hand threaded rod and this rod is right handed threaded rod. For left handed threaded rod, the threading is in left handed angle. Okay, and for a right handed threaded rod, the threading will be opposite to that of left handed threaded rod. Okay, the threading is opposite for these two. Okay, but threading for coupler nut and this coupler nut is same. Due to this type of threading, if we induce a moment at coupler, then if you induce the moment clockwise moment at coupler, then left hand this rod and this rod will get close to each other, and if we induce opposite moment, then these two rod will loosen, that these two rod will get depart from each other. Okay, now see various dimensions used in this diagram. Okay, the diameter of rod is capital D. Force P is induced. This is tensile force. DC, small dc is the core diameter of this tie rod thread. DO is the outside diameter of tie rod. Okay, this rod is known as tie rod. DO is the outside diameter of this rod. DC is the core diameter of this rod. Capital D1 is the inner diameter of coupler, and capital D2 is the outer diameter of coupler. Capital L is the length between this point and this point. Small l is the length of coupler nut. Okay, small l is the length of coupler nut. Now we will see next slide. Notations used are DC core diameter of tie rod, DO nominal diameter or outer diameter of a tie rod, capital D diameter of coupler nut, capital D1 inner diameter of coupler, D2 outer diameter of coupler, small l length of coupler nut, capital L length of coupler, small t thickness of coupler, small t1 thickness of coupler nut. So see diagram carefully. Now we will see design procedure of turnbuckle. Turnbuckle is subjected to combined loading of torsional shear stress and tensile stress. Hence, principal stresses are induced in it. So, if more than two stresses or more than one stress will act, then we have to consider the addition or cumulation of stresses, and these cumulation of stresses are known as principal stresses. Okay. So here in this case, the torsional shear stress and tensile stress is acting at turnbuckle. So we have to consider principal stress, okay, that is addition of this stress. Therefore, for the safe design of turnbuckle, we have to consider the design load, which is maximum load. Okay. So design load will be 1.3 times applied load. That is, if applied load is suppose 100 Newton, then 1.3, that is 130 Newton, is to be considered as design load. Okay, that is 30% extra load we have taken for our design purpose. Okay, for safe side we have taken a maximum load for design consideration. Here now we will see design procedure. So design load will be 1.3 times of applied load. First step is failure of tie rod under tensile stress. So see, this is a tie rod cross section. Small dc is the core diameter, small do is the outer diameter, that or nominal diameter. The tensile stress induced in the tie rod is equal to, we know that tensile stress is equal to force upon area. The force is taken as design load, and area, corresponding area here, the cross section area, HEDA area, is pi by 4 into dc square. Okay, at which the tensile stress will act, pi by 4 into dc square. Now second step, here in this from first step we will get value of dc, that is value of core diameter of this rod. Okay, now we will check the various stresses value, and check, after checking this value, we will check if this value, induced stress value, is lower than design stress value or not. If this induced stress value is higher than the design stress value, then we have to increase the parameters. Okay, the second step is failure of tie rod under shear stress. Now we have know that value of dc. So here shear stress is taken as small q, but in our book we will take shear stress value as tau. Okay, tau or tau. So tau will be equal to PD upon pi into dc into L. See, for this shear stress diagram, the area will be pi into dc means circumference, and into L means into small l. It means that it is a area of outer area of cylindrical surface. That is, circumference into length means outer area of cylindrical surface or surface area of cylinder. Okay. So PD upon pi into dc into L, small l. From that we will get small l value. Okay. Now next step, third step, failure of tie rod under crushing stress. For a crushing stress, the area is equal to, see, this is the nut and screw, and force, this part is nut part and this part is screw part. The force will act at this side. Okay, this brown color side. So see, this is the screw part, and the threading, this diameter is the diameter corresponding to this, the peak point is do, small do, and diameter corresponding to this crest point is small dc. Okay, so the hatching area will be equal to outer diameter circle minus inner circle. Okay, this area will be the hatching area, which is equal to pi by 4 do square minus dc square. Okay, so this is the whole area into small n will be number of threads into small l. Okay, so this will be total area at which the crushing stress acts. So PD upon total area, which will be equal to sigma c. Okay, if this induced stress is less than design stress, then it is okay. But if it is more than design stress, then we have to add the value of we have to increase the value of DC, that is core diameter. Okay, in step 1, if we get the value of DC, then from DC value, that is core diameter value, you can get the value of other thread parameters, that is nominal diameter, thickness of thread, then pitch diameter, that all parameters you will get from design data book. Okay, so in question, generally in exam, in question, this data is given. Okay, once in step 1 you calculate the value of DC. Suppose the value of DC is equal to 16.5 mm, and then 16.5 mm, you have to see the design data book. But in general, this required design data is given in question. So in question, check the value of DC, that is core diameter. In table, if the value 16.5 is our required value, then in table 16 mm, then 18 mm is given. So take the maximum, take the value which is nearer to the core diameter value. Okay, so 16.5 is near to the 18 mm and also near to the 16 mm, but we cannot take the less value. Okay, because our design is not safe for less value, so we can take the next maximum value, that is 18 mm. So then after selecting 18 mm core diameter value, then corresponding for 18 mm core diameter value, take the corresponding value of each parameter. Okay, that is nominal diameter will be 25 mm approximately. Okay, then pitch will be 5 mm. Likewise, you have to take it from example, that is from question. Okay, now once the value of DC is known, you will know the value of outer diameter or value of nominal diameter from that table which were given in question. Okay, so value of DO will be also known and DC will also known. Okay, from that known value, a small l value is also known, because see here, once DC value is known, calculation of DO is also easy, because these are the empirical formula for Turnbuckle. Once DC value is known, DO value can also be calculated from this empirical formula, that is DC will be equal to 0.84 DO, means DO is equal to DC upon 0.84. Okay, first we know that the value of DC, from that DO value can be calculated. Now once the nominal diameter value is calculated, the small l value can be calculated, that is DO small l value will be equal to in between DO to 1.25 DO for a steel, and in between 1.5 DO to 2 DO for a cast iron. Okay, then small n will be number of threads per mm of length, which also equal to 1 upon pitch. Okay, so pitch is given for a particular DC value. Okay, in table, so put here the pitch value, then 1 upon pitch will be value of small n. Okay, then capital D value is equal to 1.25 of nominal diameter value, 1.25 to 1.5 value, then capital D1 will be nominal diameter plus 6 to 8 mm. So 6 to 8 mm means take middle value, that is 7 mm. Okay, now later part we will discuss in next lecture.